In this Test Essentials webinar, we'll begin by looking at a few applications typically associated with a vector network analyzer. Next, we'll answer the question, how does it work, by examining the unique architectural features of a VNA, and then examine some common measurements performed by a VNA. There are a number of VNA models available on the market today, so it's worth taking a moment to examine the similarities and differences. Fortunately, every VNA has a common set of controls necessary for setting up a measurement, so we'll discuss these and then present key terms that are frequently associated with VNA measurements. We'll then examine the VNA test setup, highlighting the various components needed for calibration and measurement. Then we'll walk through the steps required to prepare a VNA for measurement, using a DUT's listed requirements as a starting point. Finally, we'll discuss VNA accessories needed to meet common test requirements, as well as options required for unconventional VNA applications. Let's get started. We'll start our presentation with a bold statement. The VNA is the most versatile and accurate instrument for measuring RF components. It is versatile because it makes all its measurements using the most fundamental type of radio frequency signal, a continuous wave. Continuous waves have constant amplitude and frequency. With a continuous wave signal, the phase is determined by the relative placement of the generator and receiver, as well as by electrical influences of the device under test. The VNA is accurate because it uses system error correction to greatly reduce the influence of unwanted losses and reflections. So the VNA's major task involves generating a continuous wave signal and measuring its amplitude and phase at different points. Most often these measurement points coincide with the ports of the device under test. But wait, there's more. The VNA can repeat these measurements over hundreds or thousands of frequency points for a wide variety of active or passive devices. Primary measurements include RF energy transmitted through a device and RF energy reflected from the ports of a device. These types of measurements are useful for impedance matching, loss measurements, which are particularly important for passive devices like transmission lines and microwave filters, gain measurements, which are important for active devices like amplifiers, and measurements of electrical delay or phase, which are very important for phased array antennas. Typical VNA applications cover all design stages, from research and development to device characterization to high-volume manufacturing test. Some common passive devices include antennas, filters, power combiners, signal splitters, interconnect backplanes, coaxial cables, connectors and adapters, and mixers. Common active devices include amplifiers, both low-noise amplifiers and power amplifiers, as well as active planar antenna arrays, front-end modules, up-down converters, as well as higher-level RF subassemblies. A VNA consists of 1, 2, 4, or more RF ports. Each one of these ports contains a reflectometer, which in modern VNAs contains two receivers, one for sampling the incident wave, called the reference receiver, and one for sampling the reflected wave, called the measurement receiver. This naturally requires a wave-separating device for sampling the incident and reflected waves. Two common devices are the VSWR bridge and the RF or microwave directional coupler. Bridges are better suited for lower frequency applications, up to a few gigahertz, whereas directional couplers provide excellent broadband performance extending from 1 gigahertz to 67 gigahertz or higher. All VNAs also require at least one RF generator or source. This generator produces a continuous wave signal at each measurement frequency. A switch or other device is used to apply the generator's output to each VNA port, one at a time. Besides these functional blocks, auxiliary components may be required for particular applications. These may include receiver as well as generator attenuators or pulse generators and modulators. How does this architecture change if you increase the port count? Basically, you need to add a new reflectometer for each additional port. Here, we show a block diagram of a 4-port device, which has 4 reflectometers. Generally, a multi-port instrument requires only a single generator for S-parameter measurements. However, extra generators are sometimes needed for advanced applications, like measuring two-tone transmitter intermodulation distortion or providing local oscillator signals for frequency converting devices. What makes a VNA's architecture so special? To understand this, we must examine individual components that make up a VNA and see how they are integrated together. For example, the VNA's reference and measurement receivers must be very linear so they can deliver accurate power ratios over wide signal levels. This is a necessary prerequisite for accurate S-parameter amplitude measurements in dB. Phase measurements, on the other hand, require coherent clocking of all receiver local oscillators. This means careful attention must be paid to the design of the LO distribution network and the placement of the receivers within the VNA so that coherence is maintained over temperature and time. The VNA receivers and generators are also tightly synchronized to ensure proper frequency settling and the fastest possible measurement speeds. Besides these internal architectural considerations, a VNA test system also generally consists of external components like test fixtures and other circuitry that can impact the electrical characteristics of the device to be tested. The VNA has no way of anticipating what is connected to its test ports, so it relies on system error correction to remove these effects. Typically, VNA calibration involves connecting test standards representing a short circuit, an open circuit, and a 50 ohm load or match to each test cable as prompted by the calibration routine, and then inserting a through standard to the end of the two test cables. Today, this process can be simplified through the use of an automatic calibration unit, also known as eCal, which contains these test standards and automatically switches between them, greatly speeding up the calibration process and reducing the chance of operator error by connecting the wrong standard during any step of this process. In this first measurement example, the frequency response of a small 7-element Yagi antenna is measured. The setup is simple. The antenna is simply connected to port 1 of a calibrated VNA, and the antenna under test is positioned in an area free of reflections or else placed in an RF test chamber. In this example, the manufacturer specifies an operating frequency range of 1850 to 1990 MHz. When measured, the VNA markers show that the return loss is better than 15 dB in this frequency range. But the return loss is purely a magnitude measurement. Sometimes phase information is desired as well. A good example is the Smith chart, which shows both amplitude and phase of reflections. A VNA allows you to electrically move the measurement plane to the antenna-driven element, which changes the resulting impedance. Here we use the offset embed function to accomplish this, and you can see how it impacts the impedance at the markers. To measure a small amplifier, the VNA may be set up as shown here. Typically, amplifier measurements require a S-parameter calibration and a power calibration with a power meter. Besides setting up a simple frequency sweep, a power sweep may be used to show an amplifier's gain compression characteristics. Here, the input power is swept from -30 to +5 dBm, and the small signal gain is seen to compress by 1 dB at an input level of 0.35 dBm. This is called the input 1 dB compression point. The VNA also displays the output 1 dB compression point of 20.5 dBm, which is simply the input compression point plus the measured compressed gain value. For this and other amplifier applications, it is wise to check for VNA receiver compression. Higher-end VNAs have mechanical attenuators built in that make this easy. Here, we increase the measurement receiver attenuation in 5 dB steps until the measured 1 dB compression point remains steady. It's also a good idea to ALC or automatic level control, especially if the application calls for high power accuracy or if the amplitude is very sensitive to drive level. Sometimes the harmonics produced by an amplifier are of interest. Here we are measuring harmonics in two ways. In the upper right-hand diagram, we are performing a frequency sweep at a fixed power level, showing how the fundamental green trace, second harmonic blue trace, and third harmonic orange trace vary with frequency. Consider that while we're sweeping the generator from 10 MHz to 5 GHz, the receiver we're using to measure the third harmonic must sweep from 30 MHz to 15 GHz, so a power calibration over this entire frequency range is required. In the lower left-hand diagram, we are performing a power sweep from -30 dBm to 5 dBm at a fixed frequency of 1 GHz. Here the green trace represents the input power, the blue trace shows the fundamental output power, the orange trace shows the second harmonic, and the red trace shows the third harmonic power. There are a wide range of VNA models available on the market today. Fortunately, they may be differentiated by only a few important characteristics. The first important characteristic is operating frequency range. Here, lower-cost models are typically limited to operation below 1 GHz, whereas higher performance models may sweep across microwave and even millimeter wave frequencies. Second, VNAs are classified by their number of ports. While some single-port VNAs exist, the vast majority of VNAs have 2 ports. With the advent of balanced circuitry and transmission lines, VNAs with 4 or more ports have become more common. Another advantage of some multi-port VNAs, like the Rohde&Schwarz ZNBT, is that they can be configured to operate in parallel mode so that the DUT test throughput can be increased for high-volume RF test applications. Another interesting application is testing of complex devices like front-end modules, which have multiple RF inputs and outputs. The final VNA classification is whether the instrument has a built-in user interface or not. Often, faceless instruments rely on the processing power of an external PC and are generally mouse-driven. Instruments with built-in screens and buttons are completely self-contained and often easier to operate on a bench. What are the key controls needed to set up and operate a VNA? An operator will usually set the stimulus type and range first. The default stimulus type is a frequency sweep, where the user establishes the start and stop frequencies or the center frequency and span. Another important stimulus type is the power sweep, which we've already seen used in amplifier measurements. For a power sweep, the user sets the starting and ending power values and also the fixed frequency at which the power sweep is to be executed. Conversely, for a frequency sweep, the fixed power level must be specified. Another important control is the number of measurement points. Since S parameters must be calculated for each measurement point, increasing this number will slow down the sweep. The receiver IF bandwidth setting impacts both the noise floor and the sweep speed. A smaller IF bandwidth reduces the noise floor and improves the instrument's dynamic range, but at the cost of a slower sweep speed. Conversely, wider IF bandwidths reduce the sweep time considerably, but at the penalty of a higher noise floor and reduced dynamic range. The final important VNA control is the calibration or system error correction method. As noted earlier, calibration is essential for removing unwanted attenuation and reflections that would otherwise degrade measurement accuracy. The most widely used and popular calibration method of the last 40 years is the TOSM, or Through Open Short Match method, also known as SOLT for Short, Open, Load, and Through. Another method gaining in popularity is the UOSM method, which is operationally very similar to the TOSM method, except that an unknown reciprocal through device may be substituted for the previously characterized through cal standard. When shopping for a VNA, here are key terms to consider for evaluating different performance metrics against your application's requirements. Frequency range. Will you need to make only in-band measurements, or are out-of-band measurements required as well? Examples of the latter might be harmonic measurements for amplifiers or the stop band performance of a bandpass filter. Dynamic range. This is a measure of the difference between the maximum power and noise floor of an instrument. Again, consider this in light of your application. If you need a wide dynamic range for a production application, you may have to sacrifice noise floor by using a wider IF bandwidth to maintain an acceptable sweep time. This might require a higher performance instrument to meet these conflicting needs. Measurement speed is intrinsically linked to your dynamic range requirements. Banner specs for sweep speed are often provided for wide IF filter settings. Also, check the fine print. Are the sweep times mentioned in the specifications based on a 1-port or 2-port calibration? Make sure you consider the values that coincide with the needs of your application. Trace noise. How much jitter is there on a trace? Less jitter is better, but often the effects of thermal noise associated with limited dynamic range will greatly outweigh the tiny values of trace noise specified on a datasheet. Measurement stability. How much measurement drift is observed over time and changes in temperature? Will you be operating the instrument in a climate-controlled environment? The sensitivity of the VNA to temperature changes, combined with performance demands of your application, may drive how often you'll need to perform calibration, hourly, daily, or weekly. Keep in mind that measurement stability is also a function of all the components in your setup, especially cables. Inexpensive or old, worn test cables can have a huge impact on measurement stability and repeatability. System error correction. Which type is best suited to your application? Does the VNA you are considering support this correction method? While most VNAs provide the TOSM method as standard, some may not support the TRL or TNA methods, which can be vital for de-embedding test fixtures from DUT measurements. What equipment is generally required for a VNA setup? The first is obviously the VNA itself, with performance suitable for the application at hand. Next, you'll need phase-stable test cables appropriate for the demands of the application. Torque wrenches must be used to ensure repeatable RF performance. These are required where the test cables connect to the VNA and also where they connect to the device under test. A cal kit is required for calibration or system error correction. Both manual cal kits and auto cals are available today. Finally, power sensors are required for applications where accurate absolute power measurements are necessary, such as with amplifier measurements. The VNA measurement process begins with setting the appropriate values of the key controls to configure the necessary measurements for the DUT. We mentioned in an earlier slide that this involves setting the stimulus type and range, power levels, number of measurement points, and IF bandwidth. Next comes calibration, which compensates for unwanted reflections and attenuation due to cables and test fixtures, and, if a power sensor is used, transfers absolute power measurement accuracy from the sensor to the VNA receivers. After completing calibration, the DUT is inspected to ensure proper DC biasing and connections. It is then connected to the VNA and measurements are made. Any required tuning, such as aligning RF filters, can be performed. Finally, trace data may be exported for archiving, for reports, or to be used in RF simulation programs. Next, we'll demonstrate this measurement process for a low-pass filter. Okay, so the first thing we're going to do is start from a preset, and now we're going to set our start frequency to 2 megahertz, and we're going to change our frequency step size to 2 megahertz. That'll give us 3,000 points. Now we're going to do a calibration with an autocal unit, and I'm just going to start the calibration sweep, doing the open short match at each port, and then we'll do a through and we'll be done. Okay, we're done, so I'm going to apply the cal, and I want to save it into our cal manager. So I'm going to add it and change the name of it to something more memorable. So I'm going to call it the 2-port UOSM cal. And now we're done here. Next thing to do, I want to remove the AutoCal unit, and I'm going to attach my DUT, which is a low-pass filter with a cutoff frequency of about 1.8 gigahertz. So I want to recall a setup I previously did for this configuration. And initially it doesn't have any calibration assigned to it, so I'm going to apply the cal that I just performed to this setup. And you can see here now I've got a marker. You can see a very nice low-pass filter response. And I can move that marker around here in the stop band a little bit to see its response. But if I couple the markers together, all the markers move simultaneously. Here I've introduced a new kind of plot called a polar plot in the lower right-hand diagram area. And this is interesting because it shows amplitude and phase of the transmission characteristic simultaneously. And you can see as I move the markers around, particularly between 1.5 and 1.7 gigahertz, we see that the phase actually changes about 45 degrees. And now I'm turning off the cal, and you can see the difference. It hardly impacts the transmission characteristic at all, as seen in the top diagram, but you can see it has quite an impact on phase. So if you're just trying to do a quick go, no-go check of the filter, you might want to just use the built-in factory calibration. But if you're interested in phase response, you really need a complete two-port cal. We've already mentioned several important accessories like phase-stable test cables, calibration kits, and power sensors. But there are a number of other measurement options that may be required for your unique application. For example, if you're measuring a frequency converting device like a mixer or down converter, or want to make harmonic measurements on an amplifier, the ZNB K4 frequency conversion option allows you to separate the generator from the receiver frequency. This capability is not required for conventional S parameters, which by definition are measured using the same generator and receiver frequency. Other active devices may require bias tees to supply DC voltage via the input or output RF test cables. More complicated test devices, like front-end modules, might benefit from a MIPI control interface, whereby the VNA itself sends commands to place the device into particular operating modes, speeding up testing. For amplifier tests, I mentioned the importance of receiver attenuators to prevent the VNA receivers from being overloaded by high input levels. For some extremely high-gain devices, additional source attenuation may be required to provide very low input power levels to the DUT. In this webinar, we've learned that VNAs are extremely versatile measurement instruments that can provide outstanding measurements on RF and microwave components and have become indispensable tools for most every RF lab bench. VNAs are commonly used for active and passive device testing in every application phase, from early development through high-volume test. The VNA has a fairly simple block diagram consisting of one reflectometer for each port. The reflectometer contains receivers for measuring the reference RF wave and the reflected RF wave, which are separated using a directional device like a VSWR bridge or directional coupler. One or more RF generators rounds out the VNA block diagram. Calibration, also known as system error correction, is very important for removing unwanted losses and reflections from the overall test setup. The minimal VNA setup also requires, at the very least, good phase-stable cables and a cal kit to ensure accurate results. This concludes the Test Essentials webinar on VNA Basics. Thanks for watching.